Niacin is far more than a vitamin that fuels metabolism. It is an active participant in the regulation of our genes and the repair of our DNA, placing it at the very heart of the body's defense against aging, cancer, and cellular breakdown. One of the most profound, yet underrecognized, roles of niacin is its impact on epigenetic regulation and genome stability. While much of modern epigenetics focuses on methyl donors like folate or compounds that directly affect gene silencing and activation, niacin quietly powers the enzymes that control DNA accessibility, repair, and expression at a foundational level. The secret lies in niacin's essential role in producing NAD+, a molecule that is not only central to energy metabolism but also acts as a substrate for enzymes like poly-ADP ribose, polymerases, PARPs, and sirtuins. These enzymes don't just help keep cells alive. They manage how genes are turned on and off, how DNA damage is repaired, and how cells respond to stress. PARPs detect DNA strand breaks and initiate repair, using NAD+ to create poly-ADP ribose, chains that signal and coordinate repair machinery. Without enough NAD+, this system slows down or fails entirely, allowing genetic errors to accumulate, a key risk factor for cancer and age-related diseases. Meanwhile, sirtuins serve as epigenetic regulators that modify histones, the protein scaffolding around which DNA is wound. By removing acetyl groups from histones in an NAD+-dependent process, sirtuins influence which genes are expressed and when. This chromatin remodeling is not random. It's tightly linked to stress resistance, inflammation control, and longevity pathways. In other words, niacin, through its support of NAD+, is directly involved in how your genes behave over time. It doesn't change your DNA code, but it influences the expression and maintenance of that code, what modern science now calls the epigenome. The implications for disease prevention, especially cancer, are profound. Cancer often begins with unrepaired DNA mutations and the loss of control over gene expression. Niacin, by enabling the repair of damaged DNA and supporting normal gene silencing, acts as a natural defense system. In fact, niacin deficiency has been shown to increase susceptibility to carcinogens and accelerate tumor formation in animal models. Yet despite this evidence, niacin rarely features in mainstream discussions of cancer prevention or epigenetic health. Instead, flashy buzzwords and newer molecules dominate the narrative, while this essential nutrient remains in the background. Similarly, in anti-aging research, the discussion often centers on telomeres, oxidative stress, and mitochondrial decline, but sirtuins, the enzymes that regulate many of these processes, cannot function without a steady supply of NAD+. And NAD+ cannot exist without niacin or its precursors. As NAD+ levels decline with age, so too does the activity of these protective enzymes, leading to faster cellular aging, increased inflammation, and loss of genomic integrity. Supplementing with niacin or its derivatives may help slow this decline, restore sirtuin activity, and ultimately extend health span, if not lifespan. Yet, once again, this connection is often lost in public discussions of longevity, where more exotic compounds get the spotlight. Even in the field of epigenetics, so often associated with cutting-edge genomics, cancer therapy, and personalized medicine, niacin remains in the shadows. It's not because it lacks relevance, but because it's too simple, too familiar, and not as marketable as proprietary interventions. This is a critical oversight. If we're serious about optimizing gene expression, preventing disease, and slowing biological aging, then we need to start giving niacin the attention it deserves. Ultimately, niacin is a master regulator of biological resilience. It doesn't just feed the engines of metabolism, it maintains the blueprints of life. Every time your cells correct a mutation, silence a rogue gene, or respond to oxidative damage without breaking down, niacin is playing a role. This is not theoretical, it's a biochemical necessity. Yet, its importance is often buried beneath newer, trendier molecules in the public consciousness. We need to rethink how we talk about vitamins. Niacin is not just a supporting player in the body's nutrition ensemble, it is a critical gatekeeper of genetic health. If you're looking for a nutrient that does more than prevent deficiency diseases, one that works at the crossroads of metabolism, repair, and gene regulation, then niacin may be one of the most powerful and tragically underappreciated tools we have.